And then we can have a look at task 34, which is about transient circuit analysis or about charging and discharging of a capacitor. So we have a circuit that consists of a voltage source. This is a DC voltage source, pretty high, 500 volts, which would not be very good for some experiments. So if I would show some experiment, I would rather scale this down to maybe 12 volts, 9 volts, 6 volts, something like this, or maybe even 5 or so. And then we have some capacitor, and we want to charge this capacitor. And for this, to limit the current at the beginning, we need to have some resistor in series. So we have a charging resistor, and over this charging resistor we charge this capacitor, so there will be a current flowing in this loop. And then at some time that we will more or less calculate, the capacitor is charged, and then we will switch over this switch to the other side, and then we will discharge this capacitor, so there will be a current going in this loop. And this is more or less what happens here. And so what we want to do now is to do some mathematical calculation of what really happens here. How do current and voltage behave during charge and discharge? And I said, because the circuit is not that complicated from an electrical engineering point of view, it's not super complicated. From a mathematical point of view, it's also not super complicated, but it's more challenging, let's say, than what we have done before. Because during or already in task A, what we need to solve here is some differential equation. And so what this is and how this looks like and so on, we will see. So let's start with subtask A. I will use blue, and maybe I can even start here. And now what we would like to do is calculate the time function or derive the time function of this voltage here, time-dependent voltage over this capacitor during the charging. So ideas how to do this.
One could use the Kirchhoff's voltage law and say Vc of t equals V source minus VRC?
Exactly. So what we can always use, if we are not sure what to do in electrical engineering, we can always set up Kirchhoff's voltage laws, or a Kirchhoff's voltage law if there is only one. We can always set up something like Kirchhoff's current laws, or if there is just one and just one law, and we would need to have the voltage current relationships at our elements. So if we set up a Kirchhoff's voltage law, in this loop it would say that the source voltage, this one here, is the same as the sum of these two voltages. If I go from this node to this node along this way, I have this voltage. If I go the other way around, I have the voltage across this charging resistor, which is also a time function, and I have the voltage across the capacitor. And they both depend on time, so I will say here these are really time functions. The source voltage is a constant voltage, so this does not depend on time, and I could rather maybe use a really capital V for this. Okay, so now we have a Kirchhoff's voltage law. Okay, what else?
Current law, current is the same everywhere?
We have just one mesh, one loop, so the current is the same everywhere. So I could say, okay, this is the same current IC of t here, at least for the charging. So we could just say, okay, IC of t is the same IC of t for the resistor and for the capacitor. Right? That does not really make sense as an equation, but okay. Current is the same everywhere, and then we need to have these voltage current relationships at our elements. So
for the resistor, it's V equals R times I.
So for the resistor, we say we just use Ohm's law. So the voltage is resistance times current. And for the capacitor,
we've also got like an Ohm's law. V of t equals 1 over c times the integral of I of t dt.
Yeah, so exactly. So we could also, I will also rather write it here at first. So we could say the voltage across the capacitor is 1 over c, and then the time, the current integrated over time. Okay, and I mean now we could take this and insert it here, take this and insert it there, and then we would get a differential, no, not really a differential equation, we would get some integral equation for the current. The unknown there then in this equation would be the current. But we want to calculate the voltage here. And we don't want to solve some integral equation, we rather would like to solve some differential equation, because solving differential equations is usually easier. I mean, at the end it does not make such a huge difference, but it's more common. People are more used to it, to solve differential equations than integral equations. Okay, so what could we do, especially with this equation, to have not this integral here, but some time derivative, for example. We just write it the other way around. So if we say the current at the capacitor is C times the time derivative of the voltage. And so if we do this for this, or if we also do this for this equation here, then the current through the resistor is the voltage drop across the resistor divided by the resistance. And then we have two equations that we can insert, let's say here and there, into our Kirchhoff's voltage law, Kirchhoff's current law. And so then we have two different voltages, the voltage drop across the capacitor, the voltage drop across the resistor, but then we can replace the voltage drop across the resistor. VRC is the same as the source voltage minus the voltage drop across the capacitor. And so if we then take this and insert this there, and if I rewrite this, so then we get on this side of the equation we get C multiplied with the time derivative of this voltage drop across the capacitor. And on the other side of the equation we get source voltage minus this voltage drop across the capacitor divided by R. And this already looks quite nice, because now we have one equation with one unknown. And the unknown is the time function of our voltage drop across the capacitor. And before, if we take a look at this here, before we had, let's say, 4 equations, 1, 2, 3, 4. Or, I mean, this is not really an equation, so let's not count this. So let's say we had 1, 2, 3 equations for 3 unknowns. 1 unknown current and 2 unknown voltages. And so, yeah, from an electrical engineering point of view, it should not be too complicated to write this down, because it's just Kirchhoff's voltage law, Kirchhoff's current law, and some current voltage relationships at the elements. And then there's already some mathematical difficulty to, from these n equations with n unknowns, to form one equation with one unknown. And this is then our differential equation that we need to solve. And let's say, the electrical engineering part of this task is already over here. And what we do now is more or less mathematics. Okay, so before solving or before continuing with the solution of this differential equation here, we would like to make this look a little nicer. So, for example, let's multiply with this r to get rid of this fraction here. So I will skip the r here and add it there. And then let's sort this a little bit so that we have all the unknowns or all occurrences of the unknown on one side and the known voltage on the other side. So then this equation will look like this, that we say there is our, I do plus this voltage. So it will cancel here and happen on the other side, appear on the other side. So we have our voltage as a function of time plus r multiplied with c times the time derivative of this voltage. And on the other side we have the known source voltage. And so this is now called some differential equation or some ordinary differential equation, and this is some ordinary differential equation of first order, because we have our function in there and the first time derivative of this function. If we would have the second time derivative, we would get a second order differential equation. And how can we get a second time derivative in this function?
With the second storing?
Yeah, we would need to have, for example, an additional inductor in our circuit, or we would need to have a second capacitor, not directly connected in series, not directly connected in parallel, but we would need to have two elements that can be charged and discharged. And yeah, it's called an ordinary differential equation or linear differential equation because we just have the function and the time derivative of the function. We don't have like the square of the function or square root of the function or something like this. And it's called some inhomogeneous differential equation because we have something on the right side. If this side would be 0, then it would be called a homogeneous differential equation. And yeah, so this, then it would be even simpler, but let's say this linear or ordinary inhomogeneous differential equation of first order is somehow the simplest differential equation that we can solve. Still, we will probably need this space and some more space on the second slide to solve this. Or at least to do it in a thorough way that is, write it down, that it's understandable and comprehensible. Okay, so even if this is some inhomogeneous equation, we will start with the homogeneous solution first. So let's take a look at the homogeneous ordinary differential equation first. And this is voltage plus R times C times, and now I will save some space by saying this with a dot, this is the first time derivative, and this now should be 0. And what is the motivation or what is the rationale behind setting the source to 0? And I mean, later on we will set the source back to the real source, but why is it still useful and helpful to take a look at this equation without the source? Because the solution of this homogeneous differential equation is, what would the circuit, what would the system do by itself if there is no source? It's like the eigensolution, the own solution of the circuit itself, without having any source. Yeah, so this is like, what would the system do by itself, and then later on we add the source. Okay. So then, how to solve this? And solving a differential equation means we would need to find a function, a time function that satisfies, that fulfills this equation. So we are not looking for a value. A solution of this equation is not a value, not some like 5 volts or so, but we would like to find a time function that satisfies this equation. And any ideas to do this?
Yesterday during lecture we used the lambda to exchange for the
and
the other one was 1.
Okay, and where did the lambda come from?
A very good question.
Very good question. So the what let's say mathematicians do in this case is they look at this with their sharp mathematic eye, and they kind of guess a solution, and later on they show that the solution that they guessed is correct. And if mathematicians do this, if they guess a solution and later on show proof that the guessed solution is correct, they call it, we do an approach. And so what we will also do is some approach. And so, of course, still we need to guess a solution. And so if we look at this and think about what does this equation tells us. The equation tells us if the function itself plus the time derivative of the function multiplied with a certain factor should always be 0. And this, of course, can only happen if the function itself and the first time derivative of the function, if they are somehow equal. Because otherwise, both together cannot be always 0 for any instant of time. So we need to have a function, we need to find a function where the function itself and the first time derivative of the function where they are somehow equal, so that they can always be 0. So, for which function this is the case?
E to the power.
Yeah, so we need to have some exponential function. And so we need to have some approach where we have e to t, some exponential function that depends on time. And why does this not work at the end? So from a mathematical point of view, I think this would be somehow okay. But from an engineering, from a physics point of view, it's not, because our time is a time, it has a unit of time, like seconds. And we can only calculate e to the power of a number, but not e to the power of a unit. So this needs to be the argument of the exponential function needs to be unitless. So we need to put something in front, like a lambda, that cancels the unit of the time. That's the idea. And so we will use this e to lambda t approach and say our voltage as a function of time is e to lambda t. And as said, the lambda, the unit of lambda will be 1 over second, so that, or must be 1 over second, so that the 1/2 and the time, they cancel their units, and we have e2 something unitless, and this will be something unitless. But what do we want to have at the end? A voltage. So what do we need to do? We need to multiply by something that has the unit of voltage, and this is this constant we will call k. You can also call it something else. I mean, in German we call it k because constant in German is Konstante. It's not written with c but with k. You could also write a c, but then it might be confused with this c or with this c and so on. I will rather call it k. I think it's also not too uncommon in English literature to call it k. And the unit of this k is 1 volt. And so because of the units, we need to have these two constants. This will cancel the time and this will add volt. So this is one motivation why we cannot just have e to the power of t, but k times e to the power of lambda multiplied with t. And there's a second rationale or a second motivation why we also, or what is another reason why we need to have these two constants there. And do you have another idea? Why do we need them? So from a graphical point of view, if we would plot this exponential function, what does the factor k do with the function?
Stretch, like.
Yeah, stretch it or squeeze it into the vertical direction. And the lambda, what does the lambda do with our time function?
Shift. Phase shift, no?
No, not really. This is what we would.
The same thing, but in the opposite.
Exactly. It also squeezes or stretches this function, but in horizontal direction. And so, yeah, also from this graphical point of view, it totally makes sense to have two constants in our solution, because these two constants allow us to make our solution fit to the problem. Because with these two functions, we can squeeze and expand the function in this direction and squeeze and expand the function in this direction. And this then also totally makes sense. Okay, so then in our equation, we don't only have this function, we also have the first time derivative of this function. So we would need to calculate the first time derivative of this function. So how do we do this?
K lambda times e.
Yeah, so we copy the k because it's a constant factor. Factor rule says us we can copy this constant factor. So then the time derivative of some exponential function is the exponential function. But it's kind of a nested function, and that's why we need to have this inner derivative. And if we just take the argument, calculate the derivative with respect to t, we get this lambda. And so now we can take this and insert it there, and let's once again take different colors. So we take this and insert it there, and we take this and insert it there, and then we get the so-called characteristic equation. And the characteristic equation is, if I just insert this at first, is k times our exponential function plus r times c times, and then the time derivative of the exponential function, which is the exponential function itself, but multiplied with lambda. And on the other side, this is 0. And so from this equation, we are able to calculate our lambda. And for this, we would need to simplify this equation a bit. So how do we simplify it?
Get rid of k and e times e to the power.
Exactly, we can divide by k because k should not be 0. We cannot divide by 0, but k should never be 0, because if k is 0, then our function would always be 0, which would be, of course, a solution of this differential equation, because 0 plus 0 is 0, but it's some trivial solution of this. So, and we can also divide by the exponential function, because the exponential function also never gets 0. And so then this characteristic equation tells us that lambda is the same as, if I bring, so here we have some 1 left. If I bring this 1 to the other side, it's a -1, and then if we divide by r and c, we get -1 divided by r and c. Okay, so we already know the lambda in our solution, and what we could maybe do in between as a quick plausibility check is to check the unit. So the unit of the resistance is ohm, and ohm is the same as volt over ampere, exactly. And the unit of the capacitance is farad, and this is the same as 1 ampere second, which is charge or coulomb divided by the voltage. And so now if we check the unit of lambda, so it's 1 over r and 1 over c, so from here we have ampere per volt, and from here we have ampere second per volt, and so the volts will cancel each other, the amperes will cancel each other, and we get 1 over second, and this is also what we said here, that we should get 1 over second for this lambda, which perfectly makes sense and fits. Okay, so now we have more or less solved our homogeneous differential equation and got this solution, and in this solution we already know lambda. So then we continue, and so solving such differential equation, it's kind of a recipe. Right? You can always, if you always do the same steps in the same order, not too much can go wrong. So the next step in the recipe is we would need to solve our inhomogeneous differential equation, this one here. And so this is the so-called particular solution and solution. And do I have some space here now? I rather need to write below this, to not write into the camera window. And so this solution, the easiest engineering way to do it, mathematicians will have other ways to do it, but the simplest engineering way is we take a look at our solution and we let time go to, or at least it works for the simple problems, we let time go to infinity. So we look at what happens if the charging would be over. And so we can do this by looking at the circuit, or we can also do this by looking at this equation. So maybe let's look at the circuit first, and we can have a second look at this equation. So if we have the source, we have this resistor, we charge this capacitor, and we wait for a long time until this capacitor is finally fully charged. So to which voltage will the capacitor be charged then?
Source voltage.
To the source voltage, because, let me write this down first, because if the capacitor is fully charged, the voltage at the capacitor should not change anymore, should be a constant voltage. And if the voltage across the capacitor is, if the voltage drop across the capacitor is constant, the time derivative of a constant is zero. So this means that the current is zero. And so if the current is zero, then we have no voltage drop across the resistor. And so the full source voltage, if there's no voltage drop here, the full source voltage must be across the capacitor. And that's why we have the voltage source across the capacitor. And the same would happen here. So if we wait for a long time, if the capacitor is fully charged, if this voltage does not change anymore, then the voltage drop across the capacitor must be the source voltage. Because once again, if this is constant, time derivative of a constant is zero. Okay, so this is our solution for this particular equation. And so now I don't have much space here. Small one. Nah, this is not working. Okay. So let's say this is the homogeneous equation, and this is, or the homogeneous solution of the homogeneous equation. This is the particular solution. So now we can write down our full solution, a little bit like with the superposition theorem. We say the voltage as a function of time is the homogeneous solution plus this particular solution, which is, as you can see, it's not really a function of time anymore. And so if I write this, it's k times e to lambda t, the lambda we know already, plus our source voltage. This term plus this term here. Solution of the homogeneous equation and solution of the inhomogeneous equation. Two parts, our exponential function and one constant part. And we are almost finished. What is missing? What is still unknown in our solution here? The k. We need to find k, and the k we get from the so-called initial condition. And the initial condition in our circuit, or the initial condition for the voltage, so the voltage at time t equals 0 is zero, because this is written somewhere in the task sheet, I would assume.
That's discharge.
An initially empty capacitor. So initially empty capacitor means that the voltage across the capacitor at the time 0 is 0. And this is just what we have written down here. Okay, so now we can insert our solution into this initial condition and say, right, it's k times e to lambda multiplied with 0 plus the source voltage, and e to 0 is the same as 1. So k plus the source voltage must be 0. So the outcome of this is that k must be minus the source voltage. And so using this, we can rewrite our solution, and now we have, let's say, like the finished solution of this problem, to say that our voltage function that we were looking for is minus source voltage multiplied with E2 minus T divided by RC plus the source voltage. And so this could be rewritten in maybe a nicer way to say it's source voltage multiplied with 1 minus E2 minus T divided by RC. And what is also, let's say, common is to say it's same equation E2 or 1 minus E2 minus T divided by tau, and then this tau is R times C, and this is called time constant of this discharging time function. And I mean, we could check that if the unit of lambda is 1 over s, 1 over second, then the unit of this tau would be really second, would be some time, so that seconds and seconds would cancel here. Okay, so this is the solution of subtask A. Calculated the time curve, the time function of our capacitor voltage during charging. So which questions do you have so far? As said, it's more or less a recipe. You can always do it the same way. And as said, the electrical engineering part is quite small. The rest is mathematics. Okay, so then we can continue with task B and take a look at what is the maximum charging current. So any ideas to solve this or to have an approach for this? When does this charging current here is maximum?
Should be at T0.
It should be at the beginning, because we said towards the end, right? If this voltage does not change anymore, then the current will be 0. So the highest charging current, or it will be 0 towards the end. We must have some current somewhere in between, and it's not something that oscillates. So the largest current should be at the beginning, and the largest current that we get. So another rationale would be, so let's say at the beginning the switch would be open, the capacitor is initially discharged or is initially empty, and we close the switch to this side. And so then we always have the voltage here of the source. The voltage at the capacitor cannot jump, because if the voltage at the capacitor would jump, we would have the time derivative of some jump is infinitely high. So we would have an infinite current, which does not make sense. So for a short moment, this voltage here still needs to be 0, but the voltage of the source needs to go somewhere. So the voltage of the source will go to the capacitor, to the resistor. And if we have a voltage across the resistor, we will have a current. And so we will have a current in this loop, and because we have a current in the loop, the voltage at the capacitor will change, will increase. So the voltage at the capacitor will increase. The total voltage will be constant. The voltage at the resistor will decrease. So the current will decrease. So there is still some current. There is still some increase of the voltage here, but it will not be that fast anymore. And so, this is the way it will continue. So we can, say our B, the maximum charging current, is the current inside this loop at the time 0, or maybe like this, at the time equals 0. And so then the question is how we can calculate this current.
V by R?
Yeah, exactly. So it's just the source voltage divided by the charging resistor in this case. Because this is just what we said, that for a short moment the full voltage drop needs to be across this resistor, and then the current is voltage divided by this resistance. Okay. Then we can continue with subtask C. After what time or which time is the charging practically finished? So what would you say, or how could we specify some time after the charging is finished?
We need to get the t of the function we had before on the left side to calculate it.
So for this one here,
for example.
Yeah, for example. So what we could do is we could do a small table and for example calculate this voltage or the result of this function for different multiples of this time constant here. So if we calculate our voltage here for tau and maybe for 2 tau and maybe for 3 tau and maybe for 4 tau or so, we can see how this changes. And so if you have not too many values, you can do it with a plain calculator. If you have, of course, Octave, MATLAB, something like this, you can also do it for more values. So I have Octave here, and I can make it a bit smaller and insert the values here. So the resistance should be 0.8 mega ohm, and mega is 10 to the power of 6, and the capacitor is 10 microfarad, and micro is 10 to the power of -6. And the source voltage, okay, we could also insert this, is 500. And so then we can calculate this time constant tau. This is R multiplied with C, and mega and micro should cancel each other, and 0.8 times 10 should be 8. So we get 8 seconds there. And so then we can say the time that we are interested in is 124 times tau. Times tau. So we get multiples of tau. And this is what we can just insert into our equation here. So Vc equals source voltage multiplied with E 1 minus exponential function, and I think I need to move this up a bit so it's not hidden behind my camera window, minus T divided by tau. And I think this should work. So now we should get 4 voltages. And so we can see that at the beginning, if we would calculate it for time equals 0, exponential function to 0 is 1, 1 minus 1 is 0, so we should start with 0. If I add, right, I think let's do it like this. So now we start with 0, then of course our time function also starts with 0. And if we would if we would wait for a very long time, we would get 500 volts. But after 4 of these time constants, or if we go to 5 time constants, right, then we are already very close to the 500 volts. So yeah, this is 316, 400 volt, 432 volt, 475, 490. And so we could wait for a very long time, but we will never really reach the 500. We will just get very close to it. But yeah, so we could say ... So after approximately 5 tau or so, capacitor is more or less fully charged. Because then it would be, right, if you have 500 volts measuring the difference with some oscilloscope, for example, between 498, 499 volts and 500 volts is challenging. Okay, and I mean, what we can do here in Octave is, of course, we could have, instead of these discrete steps or large steps, we could also say, let's take many time values between 0 and 5 times tau, maybe a 501 values, and escape the result, and so then recalculate this here again, because we will now also get 501 values. I will also escape the result, and we could plot our time function here as a function of time, and then we get this nice exponential increase and see how this capacitor gets charged. And if I would wait for longer time, so maybe up to 10 tau, recalculate and replot, and then you see, okay, then it's really getting more or less constant and voltage does not change anymore. So we could say here this would be the 5 time constants. So after, however you exact you want to have it to be, after maybe 3 time constants, 5 time constants, the latest after 10 time constants or so, it's more or less fully charged.
Yesterday during the lecture, Mr. Wick said that the convention is that after 3 tau we just consider charge. Could we just write down convention in 3 tau? Yeah. Okay.
It's just we have to. It's a matter of how precise you. So from a theoretical point of view, it will be never fully charged because you never reach the 500, but you only get closer and closer and closer to it. So the question is, how close do you want to get? And the longer you have to wait. Okay, so this does, or this solves this task C. So now we discharge. So we switch the switch to the other side and do the same thing again. And discuss what is the maximum discharge current if the capacitor is discharged via this discharging resistor here, and the discharging resistor is much smaller, it's just 0.5 ohm. So what would you do now? How would you solve this problem?
The capacitor is now the source and it should still have 500 volts.
Yeah, so if we have fully charged it, or we say, okay, the voltage here is close to 500 volts.
So the voltage has to go across the resistor and that gives us the current?
Exactly. So if we have fully charged this, 500 volts, we switch over the switch. Now we will have the 500 volts across the resistor because the 500 volts need to go somewhere. And so this maximum discharge current in task or subtask D, so I think this was called ID, and the maximum of this will be just once again the source voltage, the 500 volts, which is the same, or maybe let's write it like this, and the voltage drop across the capacitor for time went to infinity, and then divided by this discharging capacitor. And so this will be the source voltage divided by the discharging capacitor. And so we have 500 volts divided by 0.5 ohm. Ohm is volt divided by ampere. And 500 divided by 0.5 is 1000, and I don't have much space, so I will write 1 kiloampere. And we had not, I think, calculated the value here for subtask B, but if we calculate this here, 500 volt divided by 0.8 mega ohm, so also volt and volt becomes each other here, and we get ampere. And 1 divided by mega is micro, and 500 divided by 0.8
625.
Exactly. So we should get 625 microampere. And so this is now kind of interesting, and we can discuss what this might be useful for. So we have a circuit that just requires a very small current to charge, right? It's maybe also would be convenient to write this in milliampere. So we need to have a little less than 1 milliampere for charging. But we need to have, it takes like 40-50 seconds for charging. But then during discharging we can get a very high current in the kiloampere range. Question is, how long, is this some subtask? No, not really, but how long does this discharging takes place, or what would be the time constant of this discharging? We can do the same stuff here, but here it was the charging capacitor, and now we do it with the discharging capacitor. So R discharge times C, 0.5 ohm times the same 10 microfarad that we had before. Ohm times farad was second, and 0.5 times 10 is 5, and so we get 5 microsecond. So yeah, of course, if we charge with a small current over a quite long time, I mean right here this was 8 seconds. We don't have that much charge.
Maybe it's better to write resistance and discharge. Yeah.
Yeah, exactly. This is of course the discharging capacitor. A very good point. Yeah, so we take a small current, and with a small current charge over a long time. So the charge will not be super high. So if we discharge with a large current, we can only discharge for a short time. So, but yeah, we have built some circuit. It's what could be some practical use of the circuit? We have, let's say, a weak source, a source with a rather large inner resistance. Take a quite long time to charge. I mean, maybe not exactly with these values here, but let's say we have a weak source, we charge some capacitor over a long time, and then we discharge the capacitor over a much smaller load in a short time.
Laser?
Maybe some laser diode. Yeah, like some defibrillator, maybe. I'm not sure. But I think there you rather need to have a large voltage and not a large current. And okay, so we could do something similar if we would replace the capacitor by some inductor, and if we take a small resistor and a small source, charge some inductor with some current, right? The storing quantity inside some inductor will be the magnetic field, and the magnetic field is associated with some current. And then we would switch over to some large resistor in this case, and now the inductor would like to continue to push the current through some large resistance, and then we would get a large voltage. We can induce large voltages for a short amount of time, and this is how these, if you have sheep or cow, and if there's a fence, some electric fence around the cows, the cattle, and there's this voltage on the fence, on this electric fence, this is how these devices work, for example. So you take a 12 volt source, and the 12 volt would not be sufficient to do any harm to the animals. So with the 12 volt you charge some inductor, and then every 2 seconds or so you discharge this inductor over some much larger resistance, and then you get voltages in the kilovolt range, and this will be very not really dangerous, but they cause some pain. And so some practical application of this circuit here, where we take a weak source, charge this capacitor with a small current, and discharge with a high current. So we don't do small voltage to high voltage, we do small current into high current, is like here you have a cell phone, there's some camera in there, and if I say I want to do some photo with some flash, then I would like to have a high current for a short time to create this flash. If I would get the high current directly from the battery inside the cell phone is not super strong, so there might be too much voltage drop across the battery. So you take some, I don't know if it's really done this way in one cell phone, let's say, because the batteries are also super strong, but this would be some way. You have a weak battery, you charge a capacitor, and then you discharge it over a short time to get the flash for some camera. Okay, so then we can have a last look at this task E. What is the energy dissipation in the discharging resistor during discharge? So how much energy is converted here into heat, or how much energy would be converted into light if we would have this flashlight as just discussed?
We've got the formula E equals half CV squared for an energy calculation.
So say again, energy is?
Half C voltage squared.
Exactly. So we could do it this way to say the energy that goes into the resistor must be the energy that was stored before in the capacitor. And the energy stored in the capacitor is C divided by 2, or 1 over 2 multiplied with C, and then the voltage squared, and the voltage is the source voltage. Okay, so we could do this, calculate this. I will do it in Octave. So energy is C divided by 2 multiplied with the source voltage squared, and then we get some 1.25 Coulomb. not Coulomb, Joule. Yeah, and this is already quite a lot because we have this rather high voltage, let's say. Okay, would there be another way to calculate this? And if I ask like this, then for sure there is. So if we would really now calculate the energy that happens here at this resistor. So how could we calculate the energy dissipation in this resistor? And at the end, of course, it should be the same as the energy that comes from the capacitor. So how to do this?
It's ohmic, so it should be the P times T.
Yeah, so at first we say, okay, energy is, we take power, instantaneous power, and integrate power over time. And we do it from, let's say, 0 to infinity. 0 is now the 0 when the discharging starts, of course, when we switch over the switch. Okay, so then power is
U times I.
Is voltage across this resistor, the discharging resistor, multiplied with the discharging current, still integrated over time. So now we would need the voltage or this current. And we need to have the time function. So we would somehow need to go back to our calculation that we did here and do something similar like what we did here now for the discharging period. And so if we do discharging, we more or less have the very same equation. So the voltage drop across the capacitor must be the same as the voltage drop across the resistor. And so we have the same differential equation, we have the same approach, but the differential equation is homogeneous. So there is no particular solution. This will be 0. So at the end, we just have k times e2 minus tau divided by t. So we could say that for the discharging, for example, the voltage drop across the capacitor during discharging should be something like this, that we start with our source voltage and then just have E2 minus T divided by the tau for the discharging. Just some exponential function that goes down. And so this should be the same voltage, for example, here. Okay, so then we would, so this is of course also the time function, and this is, according to our Kirchhoff's voltage law, is the same voltage drop across this resistor. Let me draw this into the circuit. So, right, this is the voltage that we are talking about right now. The discharge voltage across, the voltage across this discharging resistor as a function of time. Okay, so we have something that we can insert here. What do we do with the current?
Use Ohm's law and
use Ohm's law and say this discharging current should be the same as the voltage squared divided by the resistance, is voltage divided by resistance. So here we get voltage squared divided by resistance. Okay, so I will continue here and say this is now still the time integral from 0 to infinity, and we have voltage drop across the discharging resistor as a function of time divided by the discharging resistor, and we integrate over time. Okay, and so now we can really insert this function, and 1 over r is some constant that we can already place in front of the integral. And so then what we are left is Vs squared. This is also some constant that we can later on move to the front. And we have this exponential function e2 minus t divided by the time constant of this discharge. And still we need to integrate over time, and this exponential function of course also must be squared. Okay. So let's move this to the front. Source voltage squared divided by resistance. And what can I do here with the exponential function and the square?
Write the 2 into, like 2
Write the 2 into the exponent, because e to a to the power of b is the same as, no, the b is not looking that nice, is the same as e to a times b. So we can say it's e2 minus 2t divided by tau discharge, and is still integrated over time. Okay, so then I will continue to write here source voltage squared divided by the discharging resistor. Now we need to calculate or get the fundamental function of the exponential function, or the antiderivative of this exponential function.
Minus 2 divided by tau discharge times e to the normal exponent.
Yeah, so we have the antiderivative of the exponential function is the exponential function. And now we need to divide by our inner derivative. So we have one, or we need to multiply by 1 over this, so the 2 goes to the denominator and the tau d goes to the numerator. And we also need to have this minus there, because we have a minus there. And we still have it from 0 to infinity. So next step, insert the limits. E to infinity, or e to minus infinity in this case, is 0. Or, okay, let's write it in steps. So V source divided by RD, E2, I will just write E2 minus infinity, and then minus E2 0. And this is still what we then need to multiply with the minus tau d divided by 2. And in the exponent, okay, there is still the minus 2 divided by td and so on, but infinity times something is infinity, 0 times something is 0. So E2 minus infinity is 0, as we discussed. E2 0 is 1. And so this minus and this minus, they will cancel each other. And so what we get is, if we collect this, is 1 over 2. I will bring this at first as a nice constant factor to the front. Then we have source voltage squared divided by resistance. And then we need to multiply with this time constant. And the time constant is R the discharging resistor, and this is also the discharging resistor, times C. And so what happens is that the discharging resistor and this will cancel each other, and so we, at the end, even if we have now very specifically calculated the energy dissipation in the resistor, we end up with the very same formula as the one for the capacitor, because where does the energy come from? The energy comes from the capacitor, and we need to have energy conservation, and that's why we get the very same formula at the end. Okay, which questions do you have so far? If questions come to your mind, ask questions at any time. There is one.
Just a general question. For example, in easy way, how are we able to use the complex numbers of the Bauteile of the components?
You mean like complex impedance?
Yeah. Can we measure it somehow?
Yeah, we can measure it, but it's not really connected to this task because
that's why it's a general question.
Very good point. Let's do this in not easy EDA, but let's say in LTspice, and I mean then we can somehow change the circuit a little bit, or think about how we can measure complex impedance in this case. So I will click on New Schematic, and so now we would like to repeat this calculation in LTspice. And having the switch is super complicated, so instead of having a switch, we will do a circuit for the charging, and then we will have a second circuit for the discharging. Also because the charging happens much slower than the discharging, so it would be the one has a very long time axis, the other has a very short time axis. So if we just do the charging, we need to have a voltage source. We find this here in our component and voltage. Place it somewhere here, put it to 500 volts. Then we need to have the resistor. In this way, current would go down. With Control R, you can rotate it. Current would go left, go up, go to the right, which looks good. And so we need to have the capacitor. Current goes down. This is good. I will set this to 0.8 mega. Even from the capital R, it does a lowercase capital M, it does a lowercase m. No, and this would be milli. So if you want to have mega, this is always confusing in this program, you need to have meg. You need to know this. And the capacitance is 10 micro. If you write lowercase u, it will turn into micro. So then we need to have the ground somewhere, and just need to wire with the wire tool this loop. And we are more or less finished. We can try to simulate. And now we need to set some meaningful stop time for the simulation. And because we have solved this already before, we know, okay, it's something like 40 seconds, for example, is meaningful. If we know, okay, R and C create some time constant, and R is 0.8 mega ohm, and C is 10 micro ohm. So this would be a time constant. With this curly brackets or braces around, you can do calculations. And if we take, I don't know, 5 times this, then we have 5 time constants. So now if it simulates over 40 seconds, which is meaningful. And so if I plot the voltage here, we get 500 volts. And we don't see any charging. What happens here? Anyone some idea? A problem is LTspice is fooling us, and it's already calculating some DC operating point before. And it's not really using this initial condition that the capacitor is initially empty. So it's trying to guess the solution, the the steady state solution before. So we need to go back to simulate and edit our simulation command. And there's one option here that says skip initial operating point solution. And if we activate this option, now we see nice the charging, the same time function that we have also seen here in Octave. Okay, so this would be charging, and then I say we want to have a new schematic, and in the new schematic we just use the discharging resistor and the capacitor and some ground symbol and just wire them together. Oops. And so the discharging resistor was much smaller, was just 0.5 ohm, and the capacitor is still 10 microfarad. And now we need to set the initial condition here that it was, or that it is initially charged to this 500 volts. And so you can check, there is no real option here. If you check the help, so there is something here that says IC, and I don't know if it's somewhere explained here. Yeah, so IC is the initial voltage, and this is also only used if this UIC card is, or if this option is activated, is flagged. So IC stands for initial condition, like the initial condition that we used here in our calculation. And yeah, it's a bit crude to set this, so you need to click on this with the other mouse button, and then you can say IC is 500. And so then if we run and say now, once again, we want to have maybe 5 times our discharging time here, time constant, this was 10 microfarad times 0.5 ohm. And then there's another schematic, and if I plot the voltage here, we can see, okay, how it's discharging over time, and yeah, that this happens in the microsecond range as we discussed. And so I can also have a look at the current here, and the current has the same time function, of course, because resistors, they are proportional to each other. So now if I enlarge this a little bit, maybe rearrange my windows. So here's now the nice window. So now what I could also do is I could have another trace where I take this voltage and multiply the voltage with the current. And this should give me, what is voltage times current? Is power. And it should look somehow similar, but it's just the exponential function with the power of 2 in the exponent, right? And so now we get this third y-axis here for the power in watt, in kilowatt. And so then there is a nice function in LTspice that you can integrate this over time. And I never know with which button it works. I think if you press Control on the keyboard, exactly. So if you press Control on the keyboard and click on this, I think there's also some, if you check the menu here, it says right click to edit, Control left to click, Control left click to integrate. Okay, Control left click to integrate. No, Control left click. Okay, yeah. So this is, I think, what I've done. So the integral is 1.25 joule, which perfectly makes sense. And this is also what we calculated here. No, not here. Here, somewhere. Yeah, 1.25. Okay. So then there was the question not really related to this task, and I might open up a new schematic for this. If we would do a similar calculation in frequency domain, and if we have some ohmic capacitive load. So, for example, we have this very same capacitor as before with the 0.5 mega, or more. Let's rather use the discharging one. I think this will be more useful in terms of frequency, because the other time constant is super long, and we have the 10 microfarad capacitor, and so this is our ohmic-inductive load. And so from this we would like to have complex impedance, for example. Then complex impedance is complex. How would you calculate complex impedance?
Like resistor plus 1 over J admittance?
Exactly. So if we do it for this circuit, it should be R plus 1 over J omega C. And in general, impedance is voltage divided by current. And so if the current is constant, for example, then the voltage and the impedance will be the same, or will have the same. If we set the current, for example, if the current is 1 ampere, so then the number of the impedance should be the same number as of the voltage. They should have the same value, right? Okay, so what we can do here is, because we cannot really measure directly impedance, but we can use current, or we can also measure impedance. But I think with the current source it's somehow nicer. So we use a current source to feed a current into the circuit and connect this, of course. Then we also need to have some ground symbol here. And we set this current source to 1 ampere. And not DC, because now we want to have something complex, so we set it to small signal AC analysis. This is what we do with complex phasors, set it to 1 ampere. And yeah, so now we need to simulate, and we don't want to do transient analysis, of course, we want to do AC analysis. And now the question is, what do we set here as meaningful values? So this is a logarithmic sweep over some octave, over some decade. This is a linear sweep. I would suggest to take the logarithmic sweep. But what would be a good start frequency? What would be a good stop frequency? Or what? Okay, or if you just want to have it for one frequency, of course we can select list and do it for one frequency, like 50 Hertz. And okay, there's already the result. Don't look at this. So if we go back to Octave, and if I maybe switch over to this, so our discharge, we don't have this yet, was 0.5, right? If we do it for the discharging capacitor here, for a frequency of 50 Hertz, for example. So we need to have omega. Omega is 2 times P times F, and so RD is 0.5. We have this already. So Z, the complex Z, is RD plus 1 over J over omega and C. And we get some value, this. And so if we from this calculate the magnitude, we get this value. If we calculate the phase, multiply with 180 divided by P, we get the phase. And so now if I do the calculation here, and if we would, it's better to label this node and say, okay, I will label this node with Z because the voltage at this node should correspond to the impedance, and resimulate. And we say, okay, here we get the same magnitude and the same phase as what we calculated in Octave here. And okay, now you could say this is some coincidence because let's try it. This is probably the last thing that we will do for today because we don't have much time. Let's try it for different frequency. Let's go to 5 kilohertz, for example. And so we need to recalculate omega, need to recalculate the complex impedance, calculate the magnitude, which is now much smaller, of course, because if you go higher in frequency, the capacitor will be more go into a short circuit, and the angle is also getting smaller. And so if I edit my simulation command and go from 50 Hertz to 5 kilohertz and recalculate, this is the result there. There is my Octave result. And then you can see that it once again works pretty well. And yeah, so this would be a way in Octave to, so in Octave and in LTspice to calculate these complex impedances. And of course, but this is probably a bit too much for a first or second semester electrical engineering course. We could also use this complex calculation here, or like what we do here, to at the end do the very same calculation as this one here in time domain. Have you heard of Fourier analysis, Fourier series, Fourier decomposition, something like this? But maybe you will hear in a mathematics class. And so there's a Fourier transform, and the Fourier transform connects time domain and frequency domain. And so what we could do is, and what we have more or less done right now already is, we have solved this circuit in frequency domain, which is usually much simpler because what we did here solving this circuit in time domain was quite challenging, and solving the circuit in frequency domain is much simpler, just this equation. And so one idea is to do this much easier calculation in frequency domain, then calculate this for many, many frequencies, which is, if you have a computer, it's no problem. If you don't have a computer, it's complicated, but calculate this for many frequencies, and then convert this frequency domain solution back into time domain. And if you do this, you get the very same result. But it would take us, let's say, another 30 minutes to thoroughly do it and show it in an understandable way. But this is what you need a Fourier transform for. And last short thing that we might discuss, and we have already discussed it at the beginning a little bit, what would happen if we would have a second element here, for example, like an inductor?
Secondary?
Yeah, we would get some second order differential equations, so we would get something where we have plus v dot dot. And so still second derivative can be again some exponential function. So we could use the same approach, but usually then So in the characteristic equation, you get some quadratic equation. So you get two solutions for lambda. And usually these solutions can also be complex. And having some exponential function with some complex argument means it's sine and cosine functions. So, and this also makes sense if you have a second, if you have some inductor, you can have energy bouncing back and forth between the inductor and the capacitor, and you get some resonance circuit. And so the resonance circuit will oscillate with harmonic functions, sinusoidal and cosinusoidal waves, and you will also get them from this calculation here. Everything will be much more complicated, but still it's doable. Yeah? And then you get, so yeah, it changes, but still it's somehow the same. And the idea is that, of course, if you have a sine function, the time derivative of a sine function is cosine, but the next one is minus sine. Yeah? And so this is then also what you would get if you say, okay, my function and the second time derivative of the function are equal. It must be sine and cosine functions. Yeah? And that's why exponential functions and sinusoidal and cosinusoidal functions are so important in engineering and in the natural sciences, because they are the solutions of the first order and second order differential equations.